And there's the ding dong. Right. So we were talking about global weirding. Before that, we have to talk a bit about what sets global climate. Remember, climate is basically the average conditions you can expect in any given area, as opposed to weather. Someone once said the difference is that climate is what you expect and weather is what you actually get. And we talked about the greenhouse effect, how it is necessary to keep the Earth from being as cold as the moon, but just a tiny shift in the balance of greenhouse gases can have pretty sizable effects on global climate. The other thing we've got to look at is feedback loops. And there's a lot of these in the global climate machine, positive and negative. A simple example of a positive feedback loop, this is not the only thing that affects climate, but it's one example, is a feedback loop based on albedo. Albedo is the fraction of radiation that's reflected from a surface. If the surface of the Earth was a perfect mirror, it would have 100% albedo. All of the energy hitting the Earth would reflect back off into space. If the surface of the Earth were completely covered in that Vanta black stuff, it would have 0% albedo. Albedo is very high for snow and ice, averaging 80 to 90%. I don't know how much time any of you folks have spent in seriously snowy areas, but on a bright winter day, there can be so much light reflecting from the snow that, well, that's one reason you need goggles. You can go snowblind, blinded by the glare. There we go. Because a snowy surface can reflect so much light back. And in fact, that's why snow doesn't immediately melt the instant the sun comes out. If 80 to 90% of the radiant energy hitting the snow is reflected back, that doesn't leave that much to warm the snow up, which is why you can have nice sunny days on a mountain and still not have the snow melting. Try this if you get the chance. If we get snow, find some a little bit of dark powder, like charcoal dust or something like that, if you have that lying around the house, and sprinkle a little bit of it on a snow-covered surface, and you'll see the snow that's covered in dark stuff melts a lot faster than snow that isn't, because white snow reflects so much light, but anything that's dark absorbs more light, which means it's available for making the snow melt. Right. So it's very high for ice caps. It's pretty high for clouds, average 50 to 55%, much less for water and forest. The ocean only reflects about 8% of the sunlight that falls on it, and the other 92% is absorbed. That's why the ocean looks dark and the ice caps look bright from space. That's the Earth from space. It really is a globe. No, I'm not kidding, really. And that's a view of Africa. And you can see Antarctica down at the base of the globe. And you can see that's just solid white. Africa's darker. You can see the Sahara and the Kalahari deserts. But everything in between, all that great stretch of equatorial and sub-equatorial Africa, that's all forest. Well, I guess there's some grasslands in there too, but there's a lot of forest in there, and the albedo for forest is much lower. 5 to 10% of the light shining on forest reflects back. That's why forest looks dark and ice caps look light. So when the ice caps are large, more energy gets reflected to space, right? There's more brilliant white stuff on Earth that reflects more solar energy, and that means there's less solar energy that's absorbed at the surface and sticks around. That tends to make the Earth a bit more cool. If the Earth gets a little cool, that leads to the growth of the ice caps. Okay, now that the ice caps are bigger, they reflect even more energy, and that means the Earth is even cooler at the surface because more energy is getting bounced off into space and less is available to make the Earth warm. And the Earth cooling means the ice caps get bigger, which makes the Earth cooler, which makes the ice caps bigger, which makes the Earth cooler, which makes the ice caps bigger. Each one of those reinforces the other, and we call that a positive feedback loop. The example I remember being taught of a positive feedback loop is a guy and a girl with a quiet crush on each other sitting on opposite ends of a sofa. And he decides to wriggle just a little bit closer. And she notices, ooh, he's wriggling a little closer. So she wriggles a little closer to him. And he sees that and wriggles a little closer to her. And she sees that and wriggles a little closer to him. And eventually the positive feedback loop gets, well, as my mama used to say, if they were any closer, she would have been behind him. So yeah, you could think of that as being a goofy example of a positive feedback loop. It works the same way in reverse. If the ice caps get small, more energy is absorbed at the surface and less bounces off into space. So there's more energy for heating the Earth, which makes the ice caps smaller, which means there's more energy available for heating the Earth and less going off into space, and so on until eventually there's no ice left at all. Now, obviously, since there is ice, and since the ice has not completely engulfed the planet, neither one of those is the only thing in control of climate. That's just one example of many of a positive feedback loop that affects global climate. It's thought, or it was last I looked, I might have mentioned that 750 million years ago, the Earth was covered in glaciers all the way to the equator. And last I looked, we think that once glaciers got about halfway there, the positive feedback loop just made them keep going and going and going. Any increase in the glaciers made the Earth colder, and any chilling of the Earth increased the glaciers, and the two reinforced each other until you had glaciers in Australia, which was on the equator at the time because of plate tectonics. Right. Here's another positive feedback loop. One of the things we're starting to see in Alaska is there's less sea ice. And one of the things about sea ice is that it tends to block erosion of the coastline. Since you don't have waves breaking against the coastline to carry off sediment, you just have ice going away from the coastline. That actually can slow down coastal erosion. But as temperatures have warmed, there's less ice, so there's more erosion. And there's also thawing of what used to be permanently frozen land, called permafrost. Pretty good chunks of the Arctic regions of the world, the soil is frozen solid and considered to be pretty much permanently so. But we're already beginning to see, and we have for at least 10, 20 years, permafrost areas beginning to thaw. This can be bad news for anything that you've built on permafrost, because permafrost used to be hard as a rock, and lo and behold, all of a sudden it's soft, and this can be bad news for your house or your road. And the rate of coastal erosion is increasing on the coast of Alaska. This is the village of Shishmaref, where the coast is eroded by between 100 to 300 feet in only 30 years. There was an attempt for a while to try to relocate the village, which is pretty far from everything else. I don't think there's roads in and out. And I don't think they decided to relocate the village mostly because it's very small and moving it would be extremely expensive. I'm not entirely sure what they're going to do for Shishmaref. As I said, that permafrost thawing can break up roads. That's a view in Siberia where they got some nice soil creep due to the thawing of permafrost right there. The problem is that permafrost locks up carbon dioxide and methane. To be a little bit more accurate, if your soil is completely frozen, the organic matter in it, dead plants and things like that, can't decay because it's, well, frozen, for the same reason that food in your freezer doesn't decay. As that soil warms up, organic matter begins to break down, and it begins to release more carbon dioxide and more methane. So that's another case of a positive feedback loop. The more permafrost melts, the more CO2 and methane get into the atmosphere. The more CO2 and methane are in the atmosphere, the warmer the Earth gets and the more permafrost melts, and so on. So you have a positive feedback cycle there. That's not all there is to the story, be it said, because there are negative feedback loops as well. And this is very similar to a home thermostat. If your home temperature rises and gets above a cutoff temperature, your air conditioning automatically kicks in to bring the temperature down. And then if the temperature falls below a level that you set, the heater kicks in to bring the temperature up. Your body has similar negative feedback loops. If you get overheated, your skin flushes, meaning the capillaries in your skin dilate to radiate heat away, and then you start sweating, which evaporates and cools you down. If you get too cold, you start shivering, and that generates energy to warm you up. You've got lots of negative feedback loops like this that keep the internal state of your body pretty even. They tend to bring a system back to its equilibrium state. One example is that increasing surface temperatures, the warmer it gets, the more water vapor we get in the atmosphere, and that should lead to more clouds. Clouds have a high albedo, so the more clouds we get, the more sunlight ought to be reflected away from the Earth, and that will tend to cool the Earth. Now, if this cools the Earth below a certain point, there'll be less clouds, which means less energy reflected away and more heating the Earth, which will make the Earth warm. So clouds should act like a thermostat in one of these negative feedback loops. It turns out that when you actually study this in more detail, the actual effect is more complicated than that. Clouds are neither a perfect positive or perfectly negative feedback loop because water vapor can act as a greenhouse gas. So the actual effect is a lot more complicated and not that simple, but this oversimplified is an example of a negative feedback loop affecting climate. And there's lots more. This is what makes it very difficult, just from a point of view of computation, to model what the Earth's climate is going to look like in the future. There are people that are doing it. There are supercomputers that are crunching the data as best they can, and models are constantly getting refined. But this is why we cannot absolutely say, okay, this, and this are exactly what we have to expect in the next 50 years. But we can model climate, and we can check the accuracy of climate models by looking at data from the past, looking at the Earth's history. And we can do this all the way back over 500 million years, but the methods I'm going to talk about, some of them can be used that far back, but I'll specifically talk about how we've been able to reconstruct climate over just the past few tens or hundreds of thousands of years. Remember your isotopes, same element, different numbers of neutrons in the nucleus. There's 3 major stable isotopes of oxygen. These are not radioactive. We do use radioactive isotopes of various elements for dating rocks and, of course, lots of other things. But these isotopes don't decay. Oxygen-16 is much more common. Oxygen-17 is very rare, and we don't use it here. And oxygen-18 is the third. Well, oxygen-18 atoms have 2 more neutrons than oxygen-16. That means water molecules that contain oxygen-16 weigh just a tiny bit less. That means that the kinetic energy that a water molecule containing oxygen-16 needs to escape from a puddle that it's in and go flying into the atmosphere is less. It takes less energy to make a molecule of oxygen-16 water go flying into the air and evaporate than it takes for a water molecule with oxygen-18. So if you were to take a pan of water and heat it on the stove and capture some of the water vapor would have just a bit more oxygen-16 than the liquid water that you started with. Every time you evaporate water, the water that goes into the air is a bit richer in oxygen-16 than the water it came from. So precipitation, which forms from evaporation, right? Water evaporates and then it rains down. Precipitation, rain and snow, is enriched in oxygen-16. When snow falls on land, it forms ice sheets, and those ice sheets are enriched in oxygen-16. The liquid water that didn't evaporate is enriched in oxygen-18. So at times when we've had lots of ice sheets on land, the liquid water in the oceans has been a bit more rich in oxygen-18. So the colder the climate, the more oxygen-18 is in the liquid, the oceans. The reason that matters is that things like forams, if you remember our friends, the foraminifera, like this one, have shells made out of chalk, calcium carbonate, and calcium carbonate incorporates oxygen from seawater. This little foram had to take calcium, carbon dioxide, and oxygen from its surroundings and put them together to make a shell. So the upshot is that the concentration of oxygen-18 in a foram shell should be the same as the concentration of oxygen-18 in the seawater. That means we can take this foram, grind it up, measure the concentration of oxygen-18, and use that as a guide to how cold it was on the globe when this foram was alive and making its shell. In fact, specifically, we calculate the ratio of oxygen-18 to oxygen-16. We could calculate that in the shell, and we could compare it to a standard. The standard, I believe, is a fossil that was dug up in South Carolina called the PD belemnite. Don't worry about what that is. It's not really important what it is, except it's just a standard oxygen-18 to oxygen-16 ratio, and we can compare the actual ratio in this fossil and see whether it's greater or less than our standard ratio. So that ratio of ratios is called delta 18 oxygen, or just delta 18, I think people say. And that's our thermometer. We can use that as a proxy for what global climate was at the time the shell was formed. The greater the ratio, that means the more oxygen 18 is in that shell relative to our standard. And the greater the ratio, the colder it was. And we can cross-check this against forams because we can measure this in corals, which happen to show annual growth bands. So we can tell how old a piece of coral is by counting the growth bands. That's a thin section through a coral colony, and as corals grow, they'll add a new layer every year, and you can drill tiny samples from each one of those layers and measure delta 18 oxygen. And in fact, this has been done. You can see the purple and then the green zigzag lines are measurements. And you can see it goes through an annual cycle. See, it gets higher in winter and lower in summer. We can measure this in certain mineral deposits that form in caves. If you've ever been in a Blanchard Springs caverns or something like that, you've seen stalactites and stalagmites and formations like that. We call minerals that form in caves speleothems, if you were curious. So if you can't remember whether a stalactite is the one that hangs down or a stalagmite, you can just call them speleothems, and you don't have to worry. There's other deposits of carbonate-rich rock that you can date like this. You can, of course, get data from tree rings because, you know, a tree will lay down a layer of wood every growing season. The light areas are where the tree was going rapidly, so that's your spring and summer. The darker parts of a ring are where the tree was slowing down, so that's fall and winter. And a cold or a dry year would give you a narrow tree ring, and a perfect warm and moist year would give you a wide tree ring. So you can estimate climate from that. And you can estimate global climate by drilling through glaciers and ice sheets. That's an ice core. Basically, someone drilled a big hole in, I think this was Greenland where they did this, and pulled up a core sample of ice. And in fact, they got a 2-mile-long plug of ice from the Greenland ice sheet. That's how thick that ice cap is where they drilled. That matters because ice sheets form from annual layers of snow. Every year it snows, then it may stop for a while, and then the snow comes down again, and older layers of snow pack down and eventually recrystallize into ice. Ice also traps bubbles of gas in it. You know, if you've ever looked at an ice cube from your refrigerator and noticed that it's cloudy on the inside, that's trapped ice bubbles. And those gas bubbles will let you sample the atmosphere directly. We can get, you know, maybe just a few microliters, but we can get an actual air sample from 200,000 years ago. And so we can measure the atmosphere directly there. When you put it all together, it turns out the Earth's climate does vary in 3 different cycles. That variation is caused by what we call Milankovitch cycles, after the guy who worked this out. One of the cycles is that, okay, the eccentricity of the Earth's orbit is how far it deviates from being a perfect circle. The Earth's orbit's not a perfect circle, it's an ellipse. And it actually wobbles on a cycle of about 100,000 years between being more circle and more elliptical. It'll get closer to being a perfect circle and then a little farther away and then snap back. The tilt of the Earth's axis varies from 21 to 24 degrees. I think it's now about 23. And the direction that the Earth's axis is pointing also varies on a 23,000-year cycle. All of those cycles have an effect on how much solar radiation is hitting the Earth. So you have these 3 cycles, and they're all running at different rates. And every so often, 2 of those cycles will coincide, and you'll get an especially warm period or an especially cold period, because 2 cycles will coincide, and each one will push Earth climate in the same direction. Other times, the cycles will cancel each other out. And that gives you this incredibly complicated set of climate change curves called the Milankovitch cycle. So, for example, what causes the seasons is the Earth's tilt. When it's winter, the northern hemisphere is pointed away from the sun, which means sunlight hits the northern hemisphere at a more shallow angle, and more of it gets absorbed instead of reaching the surface. It's not because the Earth is closer to the sun. In fact, in the northern hemisphere, the Earth is farthest from the sun, right in the middle of our winter. Sorry, whoops. The Earth is closest to the sun, right in the middle of our winter. Believe it's around January 5th. And the northern hemisphere is farthest away from the sun when it is our summer. So it's not the distance to the sun that causes the seasons, it's that tilt. And one of those Milankovitch cycles is the degree of tilt. When the tilt is shallower, we see less difference between summer and winter. When the tilt is steeper, we see more difference. And then the direction of that tilt also makes a difference in how much solar energy the northern hemisphere gets. And there's that Earth's orbital eccentricity. It varies from virtually a perfect circle, shown in orange, to a slightly more elliptical orbit, shown in red. When the orbit's more elliptical, I think I should have said, we have greater difference in seasons. I think that's a typo. And when you put all of these together, you get this. You can see that this is an estimate of the amount of solar energy that's hitting 65 degrees north latitude, let's say Fairbanks, Alaska, over the past million years. And you can see it swings up and down and up and down. And there are times when the swings are relatively small. If you look around the 400,000 year mark, the swings are not that big. If you look around the 200,000 year mark, the swings are a lot wider. So there are times when one of these cycles will cancel the others, and there are times when one of these cycles will reinforce another. So if you look up at the right here at the top, that's the Milankovitch cycle predictions. That line right there. If you look in the middle, that thing labeled benthic forams, that is the amount of, that's the delta oxygen. That's the delta 18 oxygen measurement for looking at benthic forams. Colder periods correspond to when delta 18 is higher. Warmer periods correspond to when it's lower. And down there below, that thing labeled Vostok ice core, that's an ice core from Antarctica, where they were able to estimate temperature directly. And you can see that those 2 middle curves match up pretty well. They both have peaks at the same point, and they both have valleys at the same point. So we're pretty clear that they're telling pretty much the same story. That there have been times when the Earth's been a lot colder, and times when the Earth has been has been a lot warmer than it is now. And they don't seem to match up quite as perfectly with the Milankovitch cycles, but you can still see they've got that same kind of zigzag shape to them. They do fluctuate on several different time scales. Those warm peaks and the cold valleys tend to come on a fairly regular basis. There is some cyclical behavior in Earth climate. The problem comes when we start looking at change on a shorter time scale. This thing that looks like psychedelic spaghetti, that is, I believe, data from 10 different ways of estimating past climate over the past 2,000 years. So over on the left of that graph is when Jesus was born, where it says medieval warm period. That's the time when the Vikings were pillaging the village, Yashur. And it was just a little bit warmer and easier to sail. Then there's a cold snap between about 1400 and 1800 called the Little Ice Age. And these different sources of data don't perfectly match up, but in general, they've got the same shape. We've got a slightly warmer period between roughly 800 and 1200. And then it gets really cool between about 1400 and 1800. The time when the Viking settlers in Greenland gave up and Iceland was almost abandoned. And then there's a humongous zigzag since up about 1850. We have shot up at an unprecedented rate since about 1800. And that's not explicable by Milankovitch cycles. If the Milankovitch cycles were all there was to the story, we might be in for another ice age, but we aren't. And so we're looking at change that we can't explain using Milankovitch cycles. This was some comparisons of, okay, what do we got? Most of those lines are computer models, predictions for what global average temperature is going to do between about 1976 and 2011. The actual measured temperatures are shown in red. That's that red kind of up and down fluctuating line. And you can see some predictions did not work out very well. That yellow straight line labeled Kellogg does not fit the data particularly well. Others do quite a bit better. The ones labeled IPCC, International Panel on Climate Change, all of those lines in green, they miss the little zigs and zags of the line in yellow, but the overall trend, they fit quite well. So those IPCC predictions have performed pretty darn well compared to actual data, a lot better than people like Easterbrook and McLean, those blue and those purple lines. So we're constantly refining our ability to make computer models of what climate is going to look like in the future. And some of them are starting to get pretty good when we compare them against actual historical data on global climate. And we're seeing real world effects. That's the summer sea ice in 2012 compared with the extent of the summer sea ice in 1979. You can see that the sea ice went all the way to the Siberian coast and all the way to northern Canada back in 1979. There was a heck of a lot less in 2012, and that's been the overall trend. There's some actual data. The gray curve is the median amount of sea ice between, I guess, the median amount of sea ice for between 1981 and 2010. The colored lines are the actual amounts of sea ice for 2016 through 2020. You can see 2020 is not finished yet. And that dashed line was the extent of sea ice in 2012. Sea ice grows in the Arctic in the fall and winter and melts in the summer. So that's why this graph, starts high and goes down, and it is at its lowest extent in September and then comes back up. And what I want you to see is that since at least 1981, the trend has been for lower and lower amounts of Arctic sea ice. It's 2012 is the lowest on record, but 2016 through 2018 and 2020, well, all the way through 2020, have all been lower than we would expect. We're seeing less sea ice every year. Well, not every year, but we're seeing an overall trend to less ice. In fact, people have started to notice things like less ice. It takes longer for the ice to form. If you are like the Inuit people that go out on sea ice, not having sea ice means you can't hunt. It may mean disruption in when animals like seals can spawn. It can mean polar bears and seals have to swim farther distances. It means the melting of permafrost, which means that buildings can shift and collapse. It means increased erosion. And the Inuit people of Baffin Island in the far north of Canada have a word for what's going on. It's ugianaktuk, which translates as not feeling like oneself. If you've ever gotten up out of bed and spent the entire day just feeling that something is strangely and horribly off and just wrong, feels like, there's somewhere in the fabric of reality, there's a screw loose and you're just not acting like you normally do, got up on the wrong side of the bed, that is ugianaktuk. And that's the way they're describing what their environment is doing right now. I don't know. I think you could argue that this whole pandemic has been one giant attack of ugianaktuk, but even the climate has been feeling ugianaktuk. Or as the New Orleans funk band The Meters wrote, the world is a little bit under the weather. Why does this matter? If you melt sea ice, that doesn't change sea level. For the same reason that if you get a glass of soda or water with ice in it and you just let it melt, when the ice melts, it doesn't cause the cup to overflow. What people are worried about is the ice sheets in places like Antarctica and Greenland. Those are melting. We've already seen evidence of the breakup of some of those big ice sheets in Antarctica. We talked about that. This is what Greenland is doing. Those areas that are shaded in blue, the blue represents areas where there is, the darker the blue, the more rapid the rate of change in the height of the ice cap. The lower the ice cap is getting. And you can see there's a lot of blue. Those are areas where melting is going on, and there's more ice melting than is being formed by snowfall. That's what has the potential to raise sea levels in a big way. If all of the ice sheets on Greenland and Antarctica melted, sea level would rise by something on the order of 100 feet. And you could pretty much kiss South Florida goodbye, to say nothing of New Orleans and Houston. We're already seeing sea level rises like that on the East Coast, although that's also coupled with some sinking of the land. But a study a few years back showed that the frequency of the streets flooding in cities like Annapolis, Maryland, which is right on the Chesapeake Bay, those streets now flood more than 3 times as often as they used to. In Miami, you've got drainage systems that run backwards and spill water into the streets whenever the tide is high. That never used to happen. The Navy's worried about this because rising sea levels are going to mess with places like Norfolk, Virginia, which is the world's largest naval base. We keep a lot of aircraft carriers in Norfolk. And remember, we talked about thermohaline circulation. Part of the Gulf Stream is pulled northwards by seawater freezing and sinking down. The North Atlantic Drift is literally dragged northward by that thermohaline circulation. Flood lots of fresh water into the northern oceans, and you shut down thermohaline circulation. That's a prediction of what you would see. Most of the world's going to get warmer, but the North Atlantic, oddly enough, would actually get colder. You'd no longer be able to send ships all the way around Norway to Russia. The weather in Scotland would be, believe it or not, worse than it already is. You'd have major disruptions to shipping if the North Atlantic, you'd lose a lot of ports, and gods only know what it would do to the marine life if the North Atlantic got colder because thermohaline circulation shut down. Okay, right, I went long a little bit, but then we started late. I will stop recording now.